Okay friends, in this lesson we're going to learn about Kirchhoff's rules. There are two rules that you have to learn. The first one is Kirchhoff's first rule, which is often called junction rule, and the Kirchhoff's second rule is known as loop rule. So we will start off with the junction rule. Now the concept of junction rule is that the current entering a junction in an electrical circuit is equal to current leaving that junction. Now, in this particular context, what is the meaning of junction? In case of an electrical circuit, every single point can be taken as a junction. It may not be a point where several conductors meet. Of course, it's possible for several conductors to meet, you will call it as a junction, sure. But even if you take any other point in a circuit, you may consider it as a junction. Now, if you put the rule into a nice little statement, this is how it goes, one of the statements. At any node or junction in an electrical circuit, the sum of the currents flowing into that node is equal to the sum of the currents flowing out of that node. So, node, junction, they mean the same. There could be any point in the circuit. Now, if you don't understand the meaning of the statement, what is the statement says? At any node or junction in an electrical circuit, the sum of the currents flowing into that node is equal to the sum of the currents leaving that node. Now, look at this circuit, you will understand this better. Look at this circuit. Here you will see a junction. You can take any point in the circuit for a junction, but let us take this particular point A. If you look at this particular point A, we call it junction A. The current entering into this junction A is IA. And the currents, there are two currents leaving the junction. One through R1 is denoted by I1, and the one through R2 is I2. So you can say, if you apply the Kirchhoff's rules, Kirchhoff's rule, first rule, or the junction rule, you can write the entering current IA is equal to sum of the leaving currents, that is I1 plus I2. Now in this particular case, the entering current is given 5.50 ampere. One of the leaving currents I2 is given 2.00 amp. Now the value of I1 is not given, but we can work it out using junction rule, because entering current will be the same as the sum of the leaving current I1 plus I2. So you can just write IA is equal to I1 plus I2. From that you can work out the value of I1 as IA minus I2, that is equals to 5.50 minus 2.00, that is equals to 3.50 amp. So I1 will be, in this particular case, I1 is equal to 3.5 ampere. There's another way you can state Kirchhoff's first rule or junction rule. This is an alternate statement. Look at this alternate statement. What does it say? The algebraic sum of the currents in a network of conductors meeting at a point is 0. What is it? The algebraic sum of currents in a network of conductors meeting at a point is 0. What does it mean by a network of conductors meeting at a point? A network of conductors meeting at a point is a junction. So this statement simply means algebraic sum of currents in a junction is 0. Now, if you want to see what exactly does it mean, take a look at this diagram, this particular circuit diagram. Take this B, this junction B. You can see in here, the current entering into junction B is I1, and there are two currents leaving the junction. They are I2 and I3. Now, when we want to use this alternate statement to describe junction rule, you have to be careful about the signs of entering currents and leaving currents. Typically, you may take entering currents as positive and leaving currents as negative. So we can apply that in here. I1 would be positive, I2 and I3 would be negative. So you can just write the expression I1 plus negative I2 plus negative I3 is equal to 0, or you may write I1 minus I2 minus I3 is equal to 0. Now suppose you want to find out the value of I1, you can take I2 and I3 to the other side. So the expression becomes I1 is equal to I2 plus I3, which is exactly the same as what you have got in the earlier statement. Now, what is the significance of junction rule? Now, the idea is pretty simple in this case. Whatever current that goes into a junction also leave that junction. So current is in fact the flow of charges. So for a stipulated time, all the charges entering into the junction should also leave the junction in an electrical circuit. It means the charges are conserved at every single point in a circuit. The charges are conserved. Whatever charges coming into a point should leave that point. No charges would get stuck anywhere in the circuit. So you can say the junction rule is a manifestation of conservation of charge. So junction rule is a manifestation of conservation of charge. If you want to make a mathematical expression for junction rule, this would help you. Look at here, sigma I in is equal to sigma I out. What does it sigma means in here? Sigma in math means sum. So I in means current entering into the junction. I out means currents leaving the junction or going out of the junction. So you can say that sum of the currents going into the junction is equal to sum of the currents going out of the junction. This is the meaning of this equation. So you say sigma I in is equal to sigma I out is a mathematical expression to describe junction rule. Now take another example. There's nothing difficult in this here. It's a very similar kind of an example. Here we have a junction A and entering current is I1 and the leaving currents are I2 and I3. So if you apply the Kirchhoff's junction rule, I1 is equals to I2 plus I3. I1 value is 11 ampere, and if you add up the leaving currents 4 and 7, you get the same value. So suppose one of these currents, for example, I3 was not given. You can find out the value of I3 by subtracting I2 from I1. So it's a very simple example, another example for junction rule. Now, let us go to the second rule, Kirchhoff's second rule, which is often called the loop rule. Now, the statement of the rule is this: the directed sum of the electrical potential differences or voltages around any closed circuit is 0. What is it? The directed sum of electrical potential differences or voltages around any closed circuit is 0. What does it mean by directed sum of electrical potential differences? Now, if you take a closed loop in a circuit, a closed circuit, there will be different components in the circuit, and every component will produce a potential difference across it. So typically you will be dealing with resistors and cells. So there will always be a potential drop across a resistor if there is a current flows through it. And every cell will produce an EMF, or rather terminal potential difference. So this is something you have to keep in your mind if you talk about directed sum of electrical potential differences. So if you work along a closed loop, the electrical potential differences across various components, the net electrical potential difference would be 0. That's the meaning of it. But you will understand this better once we get this concept of how to assign the signs for potential differences in case of resistors and cells. Take a look at these cases. Look at the first case. here, this is the case of a resistor. You know that when a current I passes through a resistor R, the potential drop across the ends of the resistor is IR. But now we have a question whether it is plus IR or minus IR. So we have to have a concept on that. Now here, suppose we take the potential difference, or you measure the potential difference in the direction of the current. Can you see this thick dark arrow? This dark arrow shows the direction of the current, and this light arrow shows the direction in which you are going to measure the potential difference. Now suppose you measure the potential difference across this resistor in the direction of the current. You can see that it is done in the direction of the current. You measure the potential difference in the direction of the current, then the potential difference should be taken as negative. What is it? If you take the potential difference across a resistor in the direction of the current, it would be negative. Now just the reverse is here. Here you can see the current is from right to left, and you are taking the directions from left to right. So actually you are measuring the potential difference. You are measuring the potential difference opposite to the direction of the current. So if you ever measure the potential difference across a resistor opposite to the direction of the current, you should take it as positive. So you understand this concept? In case of a resistor, the potential drop will be negative if it is measured in the direction of current. If it is measured opposite to the direction of the current, the potential difference will be positive. In the direction of the current, potential drop negative. Opposite to the direction of the current, potential difference is positive. That is about resistors. Now let's talk about cell. In case of a cell, look at here. It's a very similar diagram. The direction in which you are going to measure the potential difference across the terminals of a cell is from left to right. Can you see it here? Left to right. This arrow shows the direction in which you are going to measure the potential difference across the terminals of the cell. Now if you do that, this point becomes, because you can see these two ends, this shorter length, this shorter line shows negative polarity, and the longer line shows positive polarity. So this positive polarity means higher potential. So if you ever take the measurement of the terminal potential difference of a cell, and if the destination, this is the destination, if the destination is positive, then the terminal potential difference should be taken as positive. So you can see here plus E. You understand this? In case of a cell, if the destination is positive, then the terminal potential difference of the cell must be taken as positive. If the destination is positive, terminal potential difference of the cell is taken as positive. Now finally take this case. In this case again we are trying to measure the potential difference from left to right. But here we have positive terminal on the left side and negative terminal on the right side. So as we go from left to right, the destination would be negative. If the destination is negative, then the terminal potential difference of a cell is taken as negative. You can see here E is minus, negative E. So remember, in case of cell, the measured terminal potential difference is taken as positive if the destination is positive. The measured terminal potential difference of the cell is taken negative if the destination is negative. In case of a cell, if the destination is positive, terminal potential difference is taken positive. If the destination is negative, terminal potential difference is taken as negative. Now, suppose you want to have an equation or a mathematical relationship to describe Kirchhoff's second rule or loop rule. You can use this one, sigma delta V over the closed loop equal to 0.